Hi, good morning. So this is for the topics in advanced mathematics, and today we will continue our survey of the quantum field theory. Now, last time we discussed quantum field theory uh, the, in the canonical quantization procedure. And what we do is to introduce a canonical quantization condition for the field operator with pi, its conjugate momentum. And then we find that if you solve and if you write the phi in terms of A and A dagger, this A and A dagger just corresponds to the amplitude when you do the Fourier transform of the corresponding classical Kaluza-Klein field, Klein-Gordon field. Okay, sorry about that. And then you can derive that there is a simple commutation relation between A and A dagger. And then we proceed to find that this A and A dagger could add energy for one quantum, omega p, and it could add one quantum for the momentum, which is equal to the three-vector momentum. Therefore, we interpret it as the particle system. But however, in this treatment, we didn't we treat the time mostly casually. Okay, even we haven't allowed the time to appear for the so strictly speaking, we really don't have a we don't have a Klein-Gordon equation at all, because at our treatment the phi does not depend on time. Therefore, we need to introduce time into our formalism. So I say time finally. And if you remember what we treat time evolution in quantum mechanics, especially the wave mechanics, you will remember that in wave mechanics, the operator, for example, the p operator, is actually a derivative with respect to space x. Therefore, of course, it does not depend on time. What it does not, and it does not have any time evolution. What will evolve with time is the wave function. By definition, wave function depends on the space and also depends on time. Therefore, it is the time is the wave function that evolves with time. And we all know that the wave function corresponds to states. Therefore, in wave mechanics, it is the state. It is the state of the particle that evolve with time. This usually we call it the Schrodinger picture. The reason is simple because there is a Schrodinger equation first proposed by Schrodinger, which describes the evolution of time, and in its manifestation in wave mechanics, it is just the Schrodinger wave equation. Okay, so let us write this down more formally. The Schrodinger equation that treat the time evolution, give you the time evolution of state, tells you that the time evolution of a state, or if I write it as a time derivative, it is given by the Hamiltonian. So sometimes we call the Hamiltonian the generator of time evolution. So the equation is simple. Psi, the state, the time derivative of psi, the state, is equal to minus h hat times psi s. Okay, this is called Schrodinger picture. So this s, the subscript s, is just denotes what we are talking about is in the Schrodinger picture. Okay, and because the evolution, the state will evolve with time, so if we calculate the expectation value of a measurement of an operator, which is time independent, then the value of expectation value will also evolve with time. But remember, this evolution with time comes from the state. Okay, therefore, let me go a little bit more in the ordinary quantum mechanics to introduce the notation. So, Schrodinger equation. And it is obvious that this equation seems to have an exponential solution because the time derivative of something is equal to something times this per psi. Okay, so typically we will expect there is an exponential solution which look like this. Therefore, I introduce a operator that takes the state at time equal to 0 to time equal to t, which we call it u hat. It is an operator, and it depends on time, of course. Okay, so again, this u hat is the time evolution operator that moves the state from t equal to 0 to t. And of course, you expect this u will be determined by the Schrodinger equation I have just introduced. So we can just plug in this expression into the Schrodinger equation, and then, oops, sorry, like this. And then now the time derivative exists in the time evolution operator. And when you do the time derivative, it gives you h according to the Schrodinger equation. Okay, and yes, and this psi t is equal to u times psi 0. Therefore, compare this and this. It does not take much to recognize that the u, the time evolution operator, has to satisfy u time derivative equal to minus ih times u. Okay, so this why we introduce this evolution operator. The reason is that it will be this notation will be very useful when we go into interaction picture. Okay, of course you can still, but don't forget, this equation is just the Schrodinger equation. They are equivalent to each other. Okay, and as I say, this kind of equation give you an impression that the solution of u is actually an exponential function, and it is actually true. What I could so our conjecture is that there is an exponential expression for the solution, and you can check this conjecture by simply plug in the exponential minus iht into the expression of u. And it is easy to see that this exponential iht is equal to minus ih times exponential minus iht. Okay, and this second expression is just u. Therefore, you can see this exponential minus iht satisfy the equation that u must satisfy. Therefore, we say this exponential minus iht is a solution for the time evolution operator. Okay, you may ask, could we do that? Because exponential, usually we are talking about the exponential function of a number. Could we do it for an operator? Remember, this h is some complicated thing. It is an operator. We don't have any idea what it looks like. Could we do it just as if it is a number? The reason is that we could, because h is the only operator that is involved here. Okay. The only difference between an operator and a number is that a number commutes, but while operator do not commute most of the time. However, since here h does not depend on time, remember we're in Schrodinger picture, operator does not depend on time. Therefore, this operator, there's only operator involved. So of course it commutes with itself. See? Okay, therefore, treat it as a number, it is okay because there's only one operator. There's only one h here. Okay, therefore it is okay that we can took it as an exponential function. Okay, and if you are not satisfied with this answer, usually we'll go a little bit more abstract by defining this exponential minus IHT as the series, infinite series, just as if this h is a number. So you can see here. Okay, so this is actually a definition of this thing. Okay, maybe I should write it down. So this infinite series are the definition of this exponential function. Of an operator, just like this. Okay, and you can check by yourself that when you take the derivative of time with respect to this whole thing, this whole infinite series, you can get this equation. The infinite series, the time derivative of this infinite series is equal to minus IH times this infinite theory. You can check it by yourself. Just plug this into this expression. And remember, this equation here, the equal sign, this part is the only place we use the expression for exponential minus IHT. Okay, so I justify myself that we can take this exponential expression as a solution of the time evolution operator. Okay. Yeah, so we are almost done. There are some discussion about energy eigenstates. Okay, so if you are interested, you can take a look. It's useful. However, we are running a bit late. So let me go ahead and introduce the Heisenberg picture. As you know, Heisenberg is a rival to Schrodinger. So it's not a surprise that Heisenberg will create another picture. Of course, this kind of naming does not appear when these two people are still alive. So it's from us after these great gentlemen. And however, this is Heisenberg picture is a way that we do not let the state evolve, but let the operator that evolve with time. It is actually easy to see, because in quantum mechanics, only the expectation values are observable instead of the operator. Operators are operators. It's not, we don't know how to measure it. It is the expectation value that is observable. And remember, expectation value is a combination of state and operator, just like this. So I will say AT is equal to an operator A sandwiched between two time-dependent state. And then we can, using the time evolution operator we have just introduced, I can write this psi st in terms of exponential minus IHT dot psi s at time equal to 0. And the other side are the same. And therefore, I can pull this time evolution operator, or just U, together with the A hat and define this thing. This thing is another operator. However, now it depends on time. Therefore, Heisenberg say, no, Heisenberg did not exactly say this, but imagine he will say, now it is the operator that evolves with time instead of a state. Okay, and therefore I can define this time independent state psi h as the psi in Schrodinger picture at time equal to 0. See? Okay, so now in this picture, the psi, the state, does not evolve with time. But the A sandwiched between two unit evolution operator evolve with time. And I call it this thing, this as the operator in this picture. And of course, this picture is called Heisenberg picture. Remember, Heisenberg picture is totally equivalent to Schrodinger picture because they give the same prediction. So it's an amazing thing that quantum mechanics allow you the freedom to choose between them. And you will see, actually, you have infinite number of freedom to choose between Heisenberg picture and Schrodinger picture. You will see it very soon later. Okay, but anyway, Heisenberg picture. So if the A evolves with time, we would like to have a equation to describe its time dependence. Okay, so usually we call this kind of thing the equation of motion in classical mechanics. So we will also call this the equation of motion for this observable or operator. So it's easy to derive. You just plug in this A into a time derivative, and then there are two terms, only the time evolution operator that depends on time, so we can take the time derivative separately. This gives you the time derivative of this, and this gives you the time derivative of this. Okay, and after some manipulation, I hope you do it yourself instead of I doing it over the online vacuum, and it is easy to see that the first term is equal to h, because the extra h vector times a minus a times h. And this is, of course, the commutator between h and a. Therefore, this is the equation. This gives you the equation of motion for the operator, which is the time derivative of a equal to the commutator of a with respect to h. Okay, so it says again and confirm again, h is the evolution, the generator of evolution, the generator of the time evolution. Okay, and the beauty of this picture is that it is easy to go from here transit from quantum mechanics to classical mechanics. Remember that all these operator A, because remember in classical mechanics or classical physics, there is no state. There is only observable. Observable give you the description of state. Therefore, and in Heisenberg's mind, or in the mind of the Copenhagen school, the operator is the corresponds to the operator, correspond to the physical quantity observables in classical physics. Therefore, exactly the same kind of equation actually exists in classical mechanics. But in that case, the commutator is replaced by Poisson bracket. Therefore, the prescription for Heisenberg, I think Dirac is the first to point this out. But anyway, let's not go into detail. But anyway, if you have a classical mechanics and then you replace the Poisson bracket with commutator, and then you got quantum mechanics. Okay, so that's the idea. So simple and so beautiful, so elegant. That's why. So that's the way the Heisenberg, the Copenhagen school, or Heisenberg, Dirac, and Pauli Bohr will adopt in their formulation of quantum mechanics. Okay, so Heisenberg picture. Let me summarize. Oh, maybe no, there's no summarize. There's no summary, but let me summarize here that in Heisenberg picture, the state does not evolve with time. It is defined as the state of Schrodinger picture at time equal to 0. So it does not move at all. I should say it does not change at all. Okay, but the time evolution exists in operator. So it's in contrary to the the Schrodinger picture. Okay, so now let's apply these two kind of pictures to quantum field theory. Okay, actually what we did last time, if you remember, we are actually working in Schrodinger picture. Remember last time when I defined and formulate the phi operator, it does not depend on time at all. Remember? Therefore, actually, I did not say explicitly, but what is in my mind is that that's the formulation I gave you last time are actually in Schrodinger picture. But there is a very, very big shortcoming as pointed out in Tong's lecture notes. It's very bad in to work in to do quantum field theory in Schrodinger picture. The reason is simple, because it breaks the Lorentz invariance. Remember, the bottom line is that we start with a Lorentz invariant Lagrangian that give you phi, the Klein-Gordon equation, Klein-Gordon field operator that observe Lorentz invariance. However, if you quantize it and doing it in Schrodinger picture, the operator does not depend on time at all. Or you can say that it introduces a preferred time coordinates. So it's not good because the Lorentz invariant is not explicit. Okay, at least we need an operator that depends on time so that we can see, for example, Klein-Gordon equation. Okay, remember in the last presentation, we don't even have Klein-Gordon after quantization. Before quantization, of course, we start with Klein-Gordon equation. However, after quantization, we don't even have Klein-Gordon equation at all because the field operator, again, does not depend on time. Oh, but now if I have the idea of Heisenberg picture, I can easily just get Klein-Gordon equation. Let me show you. Okay, so if I do the quantum field theory, we take what we have last time and replace it with Heisenberg picture. Then the phi s, now the subscript says denotes explicitly the Schrodinger the field operator in Schrodinger picture, and therefore it does not depend on time. If you translate into Heisenberg picture, you sandwich between two evolution operator, and phi h is equal to the h at the commutator of h with phi. And then you can calculate, you can just plug in the expression of phi. And this calculation is tedious. However, I urge you to take a closer look yourself instead of doing it online. And the bottom line is, what is non-zero is this and the pi. Remember, oh, sorry. Yeah, right. So what is non-zero is this phi and pi. Remember, after we impose the quantization condition, only non-zero commutator is between the field operator and its conjugate momentum. Okay, and phi will commute with this and will commute with this. So you only need to be careful to calculate the first term, and then you get this and that and this. So the time derivative of phi is equal to pi. And the second equation, the time derivative of pi is equal to this times phi, the field operator. And therefore, if you combine these two equations together, that is, you plug in this pi into this, and you got a second derivative of t, and therefore it is easy to see. You combine the two equations together, you recover the equation of motion of Klein-Gordon. Also, the Klein-Gordon equation now actually exists in Heisenberg picture. That's the bottom line. Okay, so I here say that it is in Heisenberg picture that the field operator satisfies Klein-Gordon equation. In Schrodinger picture, there's nothing called Klein-Gordon equation. Okay, that's a very, very subtle. There is a small subtlety usually the teacher will ignore at this moment. Even I myself noticed this. On and off, and only recently. Okay, anyway. So the field operator in Heisenberg picture satisfies Klein-Gordon equation, and therefore I can write the Fourier expansion in Heisenberg picture. But here Now I can use the same argument as the last time. Last time I say that every Fourier component actually acts like a simple harmonic motion with a frequency omega p. And it is explicitly this equation because A, this operator, again, A is the Fourier expansion component of the Schrodinger picture, of the field operator. And in Heisenberg picture, it evolves with time. Here, there is no time dependence, but here, in Heisenberg picture, didn't denote a Heisenberg picture. But anyway, it's Heisenberg picture. You can recognize it from the time dependence. And according to the Heisenberg equation, this is correct. And if you work out detail, remember H is omega A dagger. And if after you plug in this expression, you get this. So A is a simple harmonic motion, okay? And therefore, the time dependence of A can be solved explicitly because it is just like a simple harmonic motion. It is exponential minus I omega pt, okay? And A dagger, you can work out the A dagger yourself. I should have put in another equation here. Anyway, so A dagger will be multiplied by exponential I omega pt. Okay, remember A dagger is the complex conjugate of A. Therefore, this is not a surprise. Okay, and then it is usually it's customary and very convenient to combine these two exponential factors into a covariant form. So I write exponential minus IPX A and plus exponential IPX. This is the Lorentz invariant form of a 4-vector inner product. Okay, and therefore this is the form. Every factors are Lorentz invariant. This is the Lorentz invariant. I will show you next time. Okay, now and A, observe this. Okay. Therefore, this phi is Lorentz invariant. It's the Lorentz invariant. Very useful. Okay, so we recover the Lorentz invariance and the Klein-Gordon equation in Heisenberg picture. There's one more thing we need to check. That is the commutation relation or quantization condition. Remember, we impose the quantization condition at time 0 or any specific time in Schrodinger picture. And now, if phi and pi now depends on time, then we have to let them evolve with time. And therefore, it could be shown that at equal time, there is a commutation relation just like this. And you can do even better by defining a Lorentz invariant commutator, which is the commutator between any phi at any space-time and phi at another any space-time. Okay, and it's not difficult to work out the result. You just need to remember that this A and A dagger has a commutation relation. You just plug in this form and this form into this calculation, and you get this. Okay, and you can show that there are very, very good property of this expression. First, it is the Lorentz invariant. Okay. Second, for time-like separation between x and y, time-like means these two space-time points could have causal relation. Okay, and therefore the commutation relation is not equal to 0. However, if x minus y is square is smaller than 0, that means that they are space separated. There is a space-like separation. Then it means you can find a Lorentz frame or an observer. You can find an observer for him. These two points are actually happen at equal time. If it happened at equal time, then their commutation must be equal to 0, phi and phi. Remember, oh, sorry, I didn't write. Phi and phi, the commutator is equal to 0. Okay. Therefore, it is, you can check, but since this relation this expression is the Lorentz invariant. Therefore, we know that it is correct. It must be equal to 0 if x and y are time-like separated, okay? Because if the 2 points are time-like separated, that means they could not have any causal relation. If they don't have any causal relation, of course, the system of phi here and the system of phi here are independent. They could not commute. They could not have any commutator, okay? Therefore, they are different systems. They are independent. Therefore, by the special relativity causality, they could not have anything to do with each other, and therefore it must be equal to 0. And it is checked here. Exactly this form is true. This form is true. This form satisfy this requirement or satisfy requirement. Okay, so the bottom line now, after this check, everything about the special the quantum field theory we like, causality, Lorentz invariance, etc. are satisfied in Heisenberg picture. So perfect. So Heisenberg picture is the perfect picture to talk about quantum field theory, or we would say the relativistic quantum mechanics. Okay, and the bottom line is that in this picture, it is easy to see that the fields are actually a system, a collection of simple harmonic motion. Okay, so it's easy to see this way. And because it is a quantized simple harmonic motion, and therefore its energy has a step structure, and therefore it corresponds to particle. That's why, again, quantum field theory is actually a particle system. Now, finally, I will start to talk about the interaction picture. Okay, up till now, we finally have a relativistic quantum field theory that describes, well, free particles. There's no interaction at all. So these pictures do not interact. They just fly by and keep on going relativistically. To describe the real world, we need interaction. So now interaction, there you go. Now, this is the Klein-Gordon free Lagrangian. And if you want to add interaction to the system, you need extra term, additional term to the Lagrangian, which usually is called interaction Lagrangian. Okay, so this is the notation. Usually it means anything not quadratic in fields. For example, phi to the fourth, or if there is a Dirac bispinner, psi bar, psi phi. Okay, something like that. Okay, and if you plug in these expression add these expression into your Lagrangian and solve the equation of motion, these terms will give you, it is easy to see, will give you extra terms which is nonlinear. So usually what we mean by interaction, it is if you stick to the wave mechanics language, they usually means nonlinear terms to the wave equation. Okay, nonlinear term to the wave equation. However, remember we are not talking about wave, so nonlinear is not the correct language to talk about this kind of thing. These terms, while nonlinear in wave picture, they actually are interaction in particle picture. Okay. Now, interaction, the Lagrangian, when I add into the Lagrangian, it must have the same contribution to the Hamiltonian. Okay, we usually call it the interaction Hamiltonian. And because the Hamiltonian is defined as this expression minus Lagrangian, therefore the interaction Hamiltonian is density, okay, is equal to minus the interaction Lagrangian density. Okay, there is a minus sign here. Okay, and therefore, yeah, that's it. Now, if we apply this kind of Lagrangian and Hamiltonian to our system and quantize it, and again, we write the A, any operator expectation value could be, if you prefer Schrodinger picture, you get this. And now if I proceed as about half an hour ago by pulling out the time evolution operator here, okay, and then now this state does not depend on time, okay. But now, because this H has a natural separation between free Hamiltonian and interaction Hamiltonian, I have a natural separation of this time evolution operator into two separate parts. Okay, I will show you explicitly how it works. However, you can naturally agree that naturally we can split this time evolution into two parts. One due to the free Hamiltonian and one due to the interaction picture. And therefore, maybe we can attribute one part to the A and one part to the psi. And therefore, we get a transition, a middle point between the Heisenberg picture and Schrodinger picture. Okay, and this kind of maneuver is easier to do by writing this expression by sandwiching A and psi with an exponential minus IH0t and exponential IH0t. Okay, and by pulling out a time evolution operator for the free Hamiltonian, I define this expression as the interaction picture operator. Okay, so that is this interaction picture operator defined as this. Here I sandwich this operator in Schrodinger picture between two time evolution operator of free Hamiltonian. This A is the operator in the interaction picture. And to compensate for this, we need to multiply the Schrodinger picture state with exponential IH0t. Of course, after multiplying this thing, it does not eliminate all the time dependence of this operator. Remember, now I have a H interaction. Therefore, I can guess this must be equal to exponential IH interaction times t multiplied by the state at time equal to 0. Okay, this I haven't proven yet. Therefore, I give you not an equal sign, but approximate sign. That's my guess, but I will show you later. It is exactly correct. Okay, now, so that's what I say. So simply by looking at this picture, so what I mean is that the operator will evolve with the time evolution from H0. The rest will stay with the H. The rest, of course, is the interaction part. Okay, so in this interaction, this is defined as interaction picture. I say it is a halfway or middle point between Schrodinger picture and the Heisenberg picture. Okay, the bottom line is that we have a natural separation of Hamiltonian into a free part and an interaction part. So why not? We attribute part of the evolution to one guy and the rest to the other guy. That's the idea. Okay, so states and operator both will evolve with time in this interaction picture. Okay, so let me summarize. So this is the time. So let me talk about the evolution of operator and the evolution of state in this interaction picture separately. First, the operator, evolution of operator. This is a definition of interaction operator. And then if you take time derivative, because AX does not depend on time, and therefore the derivation is exactly like what I did in earlier page. AI time derivative is equal to the commutator between A and Hamiltonian. No, remember, it's not a whole Hamiltonian. It is the free Hamiltonian, because here it's h0, okay? So what I say, so it is easy to observe that operators evolve just like operator in the Heisenberg picture, but with the full Hamiltonian replaced by the free Hamiltonian, okay? And therefore, the point is, for field operator, it feels free. It feels free. That is what I derived about 10 minutes ago could apply here without any revision. For example, this expansion of phi in terms of Fourier expansion exponent would look exactly like what I have 10 minutes ago. Okay, so I say the Fourier expansion of a free field is still valid. It looks like, and therefore all the good thing about the Heisenberg picture in free theory, I said before, for example, Lorentz invariance, commutator satisfy causality principle, everything is good. Okay, so boom, again, field operator are free and Lorentz invariant, as if there is no interaction. Beautiful. However, of course, the picture is not really no interaction. The interaction occurs for the states. So the second part, state. Now, the state will evolve with time because this exponential ih0t does not eliminate all the time dependence of the Schrodinger picture state. And therefore, we can do a little bit derivation. The time derivative of psi, there is two terms. First, time derivative of this exponential, it gives you this. The second, you will have a time derivative of this. Because this psi evolve, the whole Hamiltonian must be involved. So it is h0 plus h interaction. But remember, it's interaction in the S, in the Schrodinger picture. And therefore, if you combine these two terms, this annihilate with this, okay, because this evolution could pass h0 and go into here and give you psi I, so this term and this term are the same. Okay, I believe that's correct. Oh, sorry, I think there is a mistake. This is 0. Sorry, no wonder I paused. This is 0. Okay, yeah, there you go. Yeah, that's correct. Sorry, oh. Oh, sorry. No. I was mistaken. This is correct. The original expression is correct. Sorry, my mistake. Here. Oh, okay. But I'm missing one term here. Yeah, I think I'm missing one term here. My apology for being very, very clumsy here. Give me a minute to correct my mistake. That's the beauty of online teaching. At this moment, actually, you can pause and fast forward and ignore my clumsiness here. Okay, now there you go. This is correct now. So I add in a exponential minus iht0 and exponential iht0 because they cancel each other. Okay. However, this is the interaction picture of H. Remember this Schrodinger picture. However, you need to the time evolution to transform it into interaction picture. Okay, and this exponential ih0t acting on psi s according to this formula will give you the psi I. Correct. Okay. Yeah. After I first learned this, I didn't go back to check all the details until I'm teaching. Okay. Anyway, the final equation is so simple you don't really need to worry about so simple that you forgot all the derivation. Okay. So now the psi I, the time derivative of the interaction state, is equal to the H interaction. Remember, in interaction picture, not in S. Remember, if it is in S, in Schrodinger picture, then the operator does not depend on time. So this H int S does not depend on time. That's why I need to be careful about this factor, time evolution. So if this HS is sandwiched between time evolution operator, then it gives you the interaction picture of this interaction Hamiltonian. Okay, so I'm a little bit clumsy here, but it is easier for you to to see the expression and formula. It's so beautiful and simple. Okay, but the point is, let me emphasize the point. The point is, this is the interaction picture of the interaction Hamiltonian. And therefore, that means all the operators are free. Okay, for the state evolution, the Hamiltonian is free. That's beautiful. Okay, so then, so that's the interaction picture of the H in I is just the interaction Hamiltonian in interaction picture. And therefore, the few operators in this expression are free. But these free operators give you the time evolution of states. Okay, so its states evolved just like in Schrodinger picture, but with the full H replaced by interaction in interaction picture. Perfect. Okay, so this interaction picture is the thing we will use in deriving the Feynman diagram and Feynman rules. It was first proposed by Dyson in 1949. It's a beautiful, beautiful way of is a genius. Okay, Freeman Dyson. Okay, I forgot if I told you about this. Yeah, originally when we developed this quantum field theory, Feynman and Schrodinger are take two different kind of approach. Feynman used his path integral, and Schrodinger stick to the operator canonical quantization picture. And therefore, it is a confusion because these two guys use different tools to do the calculation. The benefit of Feynman's approach is Lorentz invariance. The path integral that is perfect to deal with the symmetry of the system, and therefore all the calculations are Lorentz invariant. However, on the other side, the Schrodinger, the picture are simple and very intuitive. However, the Lorentz invariance is lost when you take the canonical quantization. Okay, and canonical quantization, and therefore nobody is sure that Schrodinger's calculation is correct because nobody knows whether it is Lorentz invariant or not. Fortunately, the two guys got the same result. Okay, got the same result. So people believe they are both correct. But how? It is Freeman Dyson who solved the question by introducing this interaction picture in 1949. So beautiful. Okay. Now let me summarize this interaction picture again. Operators evolve just like in Heisenberg picture, but with the full Hamiltonian replaced by the free Hamiltonian. State evolve like in Schrodinger picture, but with the full Hamiltonian replaced by the interaction Hamiltonian. I should say by the interaction Hamiltonian with all the operators that are free. Okay, yeah. Now action. Give me 5 more minutes. I can give you the beginning of the beginning of our discussion, and I will introduce asymmetrics. Now, interaction. The key point is that now the state evolve. Therefore, we expect the state of the system in the long past could be something that evolved into something else. For example, if the two particles collide, it could become a different state. That's the picture. It could not happen in free field theory. In free theory, the two particles will just pass each other. But in interaction picture, because the state could evolve by the interaction, therefore the two particles could collide and change to a different states. So what you want to calculate is the probability or the amplitude of the system, which is something in the long past and becomes something in the long future, which I will call this thing, okay? Now, before I write it down, let me introduce the time evolution operator again in interaction picture. It's the same. It's the same in Schrodinger picture, but you need to be careful about the notation. So let me go very fast. If you have this equation, the time evolution of state, you can introduce a U, time evolution operator. I say just like in Schrodinger picture, but now remember we are in interaction picture. This time evolution operator takes the state from the time t0 to time t. So I will say psi I t is equal to this operator acting on psi at t0. That means at t0, this is the state. And using this operator, it gives you its state in the time equal to t. Okay. And it's not difficult to derive a expression, an equation that determines the evolution of U instead of the state. And the calculation is similar, or actually it's exactly the same as I give you about 1 hour ago. So the U is actually equal to minus IHI U t0. And next week, I will give you the solution of this equation. But first, before I let you go, before we finish, let me show you how important and how useful this time evolution is in interaction picture. So if the state in the, assume that a state in time t0 is psi, and now U is the time evolution operator. So it's by definition that U t0 acting on psi is the state of this guy in the future. Let me, the English is clumsy. That is, this is the state in the future that evolved from a state psi in t0. That's the definition of this. Okay, then if I take this t0 to minus infinity, that means in the long past, and t to infinity, that means the long future. This guy, this expression is the state in the long future that evolves from a state psi in the long past. So you can imagine this psi is, for example, two particles approaching each other in the long past. Okay, and this is the state after collision. But this collision could be anything. It's a linear composition of various states. And therefore, if you want to ask what's the amplitude and therefore what's the probability of this state to be measured as a state phi in the long future, then you will take the inner product of this with phi. Okay, so this is exactly the amplitude for this state to be measured as a state of phi. And remember, psi is the state in long future. After collision, in the future, it becomes a linear composition. And you ask detector, detected, it becomes a certain state phi in the long future. So if you multiply, take inner product of these two, it gives you the amplitude. And square it, you get the probability for this thing, this interaction, this collision to happen. That is from a state of psi. In this picture is the two strawberries colliding each other into a state of phi. That is a state with a lot of strawberry and the pear and the banana, blah, 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 and egg points. Okay, so that's exactly what we measure in particle detector. Okay, so the amplitude for this whole sequence equal to this. This is a matrix element. So for example, let me give you an example before I let you go. For example, the transition amplitude for decay of A going to BC, of course, in the long past, it is A. In the long future, it's BC. So if you sandwich U between A and BC, it gives you the amplitude. Again, if the process you are calculating is the scattering AA going to BB, then in the long past, it is AA. In the long future, it's BB. So you, again, sandwich U between AA and BB. I can say that slowly. AA in the past after evolution, so this part is the state in the long future. And if you want to ask how much probability or what's the amplitude you will observe this sky as BB, then you take the inner product. Okay, and then you got this. So the amplitude is the corresponding, we usually call matrix element of this operator. This is the matrix element of this operator between AA and BB. Okay, so therefore this U control everything. U would give it a new name, not U itself, but U minus infinity to infinity. We call it S operator. So I would say S operator is the key object in particle physics. Okay, yeah, beautiful. So next week, I will try to tell you that how we are going to deal with this S. S operator cannot be solved explicitly, but it can be calculated in perturbative expansion. And there are some beautiful details I'm going to tell you next week. You can, of course, check the transparency I posted. I sent it to you, and I will post it on the Moodle and the course website probably tonight. There is a seminar today, so probably post it tonight. Anyway, you can check if you are curious about how we are going to deal with this monster S. Actually, it's very, very simple, and the bottom line is that it just corresponds to the Feynman diagram, and the result is a Feynman amplitude. Okay, so that's it for today. I will try to do it during the weekend so that you can see this online presentation earlier. Okay, but I hope I have the time and the energy. But anyway, see you next week. Bye bye.